Welcome to the Deep Dive. We're here to slice through complex topics, getting at the insights that, well, that really matter. Today, we're embarking on a pretty fascinating journey, right into one of the most fundamental processes. It governs our very existence. Fuel metabolism. We're drawing our insights from a really rich section of Marks's Basic Medical Biochemistry, a clinical approach. Our goal is to distill its core wisdom into something engaging, something clear. Our mission today, it's really to cut through the intricate mechanics of how your body handles energy. How it eats, how it stores, and how it burns fuel. Think of it like decoding your body's most essential economic system. We're going to try and make sense of these, well, sometimes dizzying biochemical pathways that orchestrate everything, and maybe most importantly, we'll connect them directly to their real-world impact on your health, hopefully giving you some of those genuine aha moments. So get ready to see how the food you eat quite literally powers your life, and what happens when this incredibly sophisticated system maybe hits a snag. So let's kick off this deep dive.
Let's think about the absolute fundamental challenge our bodies have faced for, well, millennia, ensuring our survival. And it really boils down to two critical needs. First, we must be able to build everything our cells require that isn't directly supplied by our diet. Simple as that. And second, we have to protect ourselves from an ever-changing environment. That could be, an unpredictable food supply or maybe exposure to potential toxins, the constant balancing act, a dynamic one.
That's spot on. And to meet those two foundational requirements, our bodies have evolved with a really sophisticated network of metabolic pathways. Think of them as the pillars of our metabolic survival, all working together in concert. First, we have fuel oxidative pathways. These are essentially your body's power plants. They take the food you eat, the fuel, and convert it into usable energy, ATP. It's how every single cell in your body gets its juice.
Power plants, I like that.
Then come the fuel storage and mobilization pathways. Now, these are absolutely critical for survival, especially, thinking back before supermarkets existed. They allow us to stash away energy when food is plentiful, sort of like a squirrel saving nuts for winter, and then strategically release it when we need it most, say, between meals, overnight, or maybe during a burst of activity. Next up are the biosynthetic pathways. These are our body's construction crews. They're constantly building the complex molecules our cells need to function and grow. We're talking about new proteins, essential fats, the building blocks for DNA, all crafted from simpler components. It's quite amazing.
The construction crews, yeah.
Yeah. And finally, we have the detoxification and waste disposal pathways. This is your internal cleanup crew working tirelessly 24/7. They neutralize and eliminate harmful substances, whether they come from the environment or are just the natural byproducts of our own metabolism. It's a beautifully integrated system, really is.
I love that imagery. The power plants, the storage crews, the construction teams, the cleanup crew. All distinct, yet perfectly synchronized.
Yeah.
To really grasp this, maybe let's visualize a kind of metabolic roadmap, just a conceptual flow. Imagine all the dietary components you consume. Carbohydrates, fats, proteins. They enter your body, go through digestion, get absorbed, travel through your bloodstream, and eventually become these fundamental compounds in cells, like raw materials arriving at a very busy, highly organized factory.
Exactly. And once those compounds and cells are in place, our conceptual map shows them branching off. Different fates, each pathway serving a vital purpose. Some of these compounds, they get immediately routed into those biosynthetic pathways to construct new cellular components. Constant renewal, constant building. Others are channeled into fuel storage pathways, becoming your body's reserves. Think glycogen in your liver or fat in your adipose tissue, just waiting patiently for later use. And a substantial portion, well, that enters those fuel oxidative pathways we just talked about, the engines. Here, the compounds are burned, ultimately producing carbon dioxide and water, pretty harmless byproducts, but most importantly, generating energy, ATP. And of course, any metabolic waste from all these processes is diligently handled and eliminated by our detoxification and waste disposal teams. Can't let that stuff build up.
That energy aspect is the absolute linchpin here, isn't it? It's not just some abstract idea, it's the lifeblood, the literal currency our cells operate on. And this brings us directly to that really elegant concept, the ATP-ADP cycle. It sounds complex, but it's maybe the most efficient energy recycling system imaginable.
Yes. ATP, or adenosine triphosphate, is unequivocally your body's universal energy currency. No question. Think of it like a rechargeable battery, a tiny molecular one. When our cells perform energy production, breaking down carbohydrates, fats, even proteins, the energy liberated from those processes is precisely what's used to regenerate ADP. It's created by adding an inorganic phosphate, we can just call it pi for short, back onto adenosine diphosphate, or ADP. So you take a spent battery, the ADP, and you recharge it with energy to get ATP back.
Charging it back up.
Exactly. Then, that newly charged ATP battery powers this astonishing array of energy utilization processes throughout your body. This includes everything. Vital tasks like building new molecules through biosynthesis, detoxifying harmful compounds, the incredible contraction of your muscles, even the active transport of molecules across cell membranes, and just the simple act of generating body heat, which is a process called thermogenesis. Now, when ATP powers these activities, it releases its stored energy, it converts back to ADP and pi, and it's immediately ready to be recharged again. The really profound insight here is that this isn't just a cycle of spending energy, it's this elegantly designed, perfectly recyclable battery system. It's, you could say, evolution's masterstroke in efficiency. It allows life to persist without needing a constant new raw energy input right at the cellular level. It's why your cells can function continuously, second by second.
So the food we eat, it truly is the raw material that keeps this incredible cycle humming along. We often talk about macronutrients and micronutrients, and it's probably important to differentiate them quickly. The macronutrients, that's your carbs, fats, and proteins, they provide the bulk of our energy and the actual building blocks for our cells. But the micronutrients, things like vitamins and minerals,
Yeah.
well, they don't provide calories, but they're just as essential.
Absolutely essential. They're like the tiny precision-engineered gears and catalysts. They ensure the entire metabolic machine runs smoothly, enabling all these large-scale processes. You can't run the factory without the little parts working.
Makes sense.
Precisely. And within those broader metabolic pathways, we can categorize them further. Catabolic pathways, those are the breaking down processes. Think of our fuel oxidative pathways. They release energy by disassembling larger complex molecules into simpler ones. They basically break fuel apart. On the other hand, anabolic pathways are the building up processes, like our biosynthetic pathways. They create larger, more complex molecules from smaller ones. And crucially, these processes require an input of energy, typically from that ATP battery we talked about.
Building requires energy, breaking down releases it.
Exactly. A great example is synthesizing proteins from individual amino acid building blocks that takes energy. It's like constructing a house brick by brick. You need energy for that.
It's just astonishing how exquisitely all this works in concert, seamlessly. And for that concert to play harmoniously across the entire body, communication has to be absolutely crucial.
Oh, completely. Our bodies have incredibly sophisticated systems for communication between tissues. It's not just one organ doing its own thing. This is facilitated not just by transport pathways shuttling molecules around, but especially by intricate intracellular signaling pathways. Think hormones. Hormones act as these molecular messengers, coordinating all these complex metabolic activities throughout your entire body. They ensure everything stays in perfect balance, responding to your body's moment-to-moment needs, like, okay, we just ate, time to store, or, uh-oh, running low, time to release.
Okay, let's unpack this a bit more. Where does all this essential fuel actually come from? We've talked about our body's need for energy, but what are the primary sources we actually put into the system? From our plates. This brings us right to the concept of dietary macronutrients as our primary energy sources, the big three.
Right, our dietary fuels are quite literally the foundation of our energy. First up, carbohydrates. These come in many forms. You've got complex polysaccharides like starch found in plants or glycogen, which our own bodies store. Then there are disaccharides like common table sugar, sucrose, or milk sugar, lactose. And ultimately, they all get broken down into monosaccharides, single sugar units. Think glucose, fructose, and galactose. Of these, glucose is the predominant sugar circulating in your blood. It's a true star player in your body's energy economy.
Main one.
Definitely. Now, when carbohydrates are burned or oxidized for energy, they yield approximately 4 kilocalories per gram, or kcal. That's a key number to remember. 4 kilocalories for carbs. Next, we have proteins. These are basically linear chains of amino acids, intricately linked together by peptide bonds. Proteins are fascinating because, beyond their critical structural roles building tissues and enzymatic roles running reactions, they contain about 16% nitrogen by weight. This nitrogen content has important implications when they're metabolized, especially for how your body handles waste, getting rid of that nitrogen safely.
Right, that urea cycle thing.
Exactly. And like carbohydrates, proteins also yield approximately 4 kilocalories when oxidized. Same energy yield, roughly. And then we have fats, primarily consumed and stored as triacylglycerols, sometimes called triglycerides. Picture their structure. You have 3 fatty acids. Common ones might be palmitate or oleate attached, esterified, to a single glycerol molecule backbone.
3 fatty acids on a glycerol. Got it.
Correct. Now here's where fats truly stand out for energy. They're by far the most energy-dense fuel. They yield approximately 9 kilocalories when oxidized,
Wow, more than double.
more than double the energy per gram compared to carbohydrates or proteins. This profound difference isn't just a chemical curiosity. It's why our bodies, honed by millennia of potential scarcity, are optimized to store fat. It's a high-capacity, low-water fuel tank. This incredible survival mechanism, though, is now kind of challenged by the constant availability of food in many modern diets.
Our biology hasn't quite caught up with DoorDash, maybe?
Something like that. And just to briefly acknowledge it, alcohol is another caloric component we might consume that provides energy. It yields approximately 7 kilocalories. So it places it somewhere between carbohydrates, proteins, and fats in terms of energy density. Hashtag B, body fuel stores what we save.
So we've established how energy-dense these fuels are.
Yeah.
4, and 9 kilocalogram, roughly. But here's where it gets really compelling for me. If we're not constantly eating, how do we keep going? Our bodies are incredibly clever at saving fuel, aren't they? We don't just burn it. We're masters of storage.
Absolutely. Our bodies are expert fuel hoarders. They're built for survival in times of potential scarcity. We have 3 main fuel storage forms. First, glycogen. This is a highly branched polysaccharide, basically many glucose units strung together and branched out. It's stored primarily in 2 locations, your liver and your muscles.
Liver and muscle, different jobs.
Different jobs, exactly. Liver glycogen's main function is to maintain stable blood glucose levels for the entire body, especially for your brain, which is a huge glucose consumer. Muscle glycogen, on the other hand, is a bit more, let's say, self-serving. It provides fuel specifically for the muscles that store it. Crucial during physical activity, muscles keep their own stash. Then there's triacylglycerol, which we usually just call fat. This is by far our major form of stored energy, tucked away predominantly in your adipose tissue or body fat. And remember, it's significantly more energy dense than glycogen. Think of it as your long-term, high-capacity fuel tank, ready for an extended journey without refueling.
The main energy reserve.
Unquestionably. Lastly, we have protein. Now, protein serves absolutely critical structural and enzymatic roles throughout your body. It builds and runs pretty much everything. But it can also be pressed into service as a fuel source, primarily by breaking down muscle protein. However, and this is vital, protein is not a primary storage form like fat or glycogen. When your body starts degrading protein for fuel, it often has serious functional consequences because you're literally breaking down essential cellular machinery or muscle tissue. It's a last resort, ideally.
Okay, so it's not just sitting there waiting to be burned, like fat is.
Precisely. To give you a real sense of scale, let's consider an average 70-kilogram man, about 154 pounds. His glycogen stores are relatively modest, maybe 0.4 kilograms in muscle, and only about 0.08 kilograms, like 80 grams, in the liver. Not much, really. Protein is significant, maybe around 6 kilograms, but it's doing all sorts of other jobs. But triacylglycerol, fat, it absolutely dwarfs them all. Typically coming in at approximately 15 kilograms, maybe 33 pounds or so, that accounts for a staggering 85% of the total stored calories in the body. The real aha here is realizing our bodies are hardwired to prioritize fat storage. It offers the most energy bang for its buck, and it takes up relatively little space, especially compared to glycogen, which stores a lot of water with it. Perfect for long-term survival.
That's a huge disparity. 85% of stored calories in fat. It really underscores the critical importance of adipose tissue, our body fat, as the body's primary and most efficient long-term energy reserve. A marvel of biological engineering, really. Storing substantial fuel with relatively little water, making it compact and effective for navigating periods without food. Hashtag pre. Daily energy expenditure, how we burn. So if we know how much energy is in our fuel and how much we store, what does this all mean for how much fuel we actually need each day, how much we're burning? This brings us to the concept of daily energy expenditure, essentially. How much energy your body is using just to exist and function over 24 hours.
Right. Your daily energy expenditure, DEE, is the total amount of fuel your body burns or consumes over a 24-hour period. It's comprised of 3 main components. The first, and often the largest chunk, is your basal metabolic rate, BMR, sometimes called resting metabolic rate or RMR. They're very similar. This is the baseline energy your body needs just to keep your involuntary bodily functions running while you're completely at rest. Physically and mentally, we're talking about the non-negotiables: breathing, your heart beating, the incredible electrical activity of your brain, maintaining crucial ion gradients across cell membranes, essential repair, synthesis, the cost of simply being alive.
The basic running costs.
Exactly. BMR is typically measured under very specific controlled conditions. In a comfortably warm room, usually 12 to 18 hours after your last meal, so you're post-absorptive, and with you awake but lying perfectly still. Several factors influence your BMR. For instance, a larger body size generally means a higher BMR. More tissue takes more energy. Having more muscle mass compared to fat also increases BMR, since muscle is more metabolically active even at rest. Age plays a role too. BMR tends to decrease slowly as we get older, and things like fever or hyperthyroidism can significantly increase BMR. Pregnancy and lactation also boost it.
So it varies quite a bit person to person.
Definitely. The second component of DEE is physical activity. This is all the energy you expend moving your body, everything from fidgeting to running a marathon. The amount varies dramatically, as you'd expect. For example, someone with a mostly sedentary lifestyle, maybe a student or office worker, might find their physical activity adds about, say, 30% to their BMR. But someone engaged in heavy physical labor or intense athletic training could easily double or even triple their baseline energy needs through activity. It's hugely variable.
That makes sense. Activity level is key.
And the third component is diet-induced thermogenesis, DIT. This is also known sometimes as the specific dynamic action, or SDA. It's the energy your body expends specifically for the processes of digesting, absorbing, distributing, and storing the nutrients from the food you've just eaten. Think of it as the energy cost of processing your fuel. It's not free to handle food. It typically accounts for about 10%, maybe a bit more or less of the calories you actually ingest.
So, okay, if we put all that together, the BMR, the activity, the DIT, we can actually start to estimate someone's daily energy needs. The text gives us some really illuminating examples of this.
It does, and it brings these calculations to life. Consider Ann R., one of the cases. As part of her diet analysis, she consumed only 615 calories per day. Very, very low. Then there's Ivan A., who consumed a substantial 4,110 calories per day, and the text breaks it down. His 585 grams of carbs gave him 2,340 kilocal, 150 grams of protein added 600 kilocal, 95 grams of fat yielded 855 kilocal, and even 45 grams of alcohol contributed 315 kilocal. Adds up quickly.
So you can see the input side clearly.
Right. And the source also shows us how to calculate the output side, the DEE, more comprehensively. For Ivan A., who was a 264-pound or 120-kilogram male, his basal metabolic rate was calculated using an equation the Mifflin-St. Jean is common. His BMR came out around 2,880 kilocal a day. Now, if we assume a sedentary lifestyle for him, his physical activity might add about 30% to that BMR. So his total daily energy expenditure would be approximately 3,744 kilocal a day.
So he was eating more than he was burning based on that activity level.
Based on that sedentary assumption, yes. It highlights how vastly individual energy needs can be and how lifestyle impacts that balance. Hashtag D, healthy body weight and nutritional balance.
So with all this talk of energy in and energy out, calories consumed versus calories burned, how do we know if we're in the healthy zone when it comes to weight? It's a huge question for so many people.
It is, and for practical purposes, a widely used measure is the body mass index, BMI. It's calculated as your weight in kilograms divided by your height in meters squared, kg/com. It gives us a general classification. Typically, underweight is considered below 18.5, healthy weight ranges from 18.5 up to 24.9, overweight is 25 to 29.9, and then obesity is generally categorized into classes. Class 1 is 30-34.9, Class 2 35-39.9, and Class 3 is 40 or above.
But you hear criticisms of BMI, right, like for athletes?
Oh, absolutely. And it's crucial to remember these are general guidelines. BMI doesn't account for body composition. A very muscular person might have a high BMI due to muscle weight, not excess fat. However, it remains a clinically useful tool for screening purposes and looking at population health trends, even with its limitations. At its core, weight management is fundamentally a matter of caloric balance. It sounds deceptively simple, though we know the practice is complex. If you consistently consume more energy than you expend, you gain weight. If you consistently expend more energy than you consume, you lose weight. That's the basic physics of it. Our source notes that 1 pound of adipose tissue, or body fat, is roughly equivalent to about 3,500 calories, or kilocalories. This means that to lose, say, 1 to 2 pounds per week, a generally recommended sustainable rate, you typically need to create a consistent caloric deficit of about 500 to 1,000 kilocalories per day through diet, exercise, or both.
500 kilocal deficit a day for a pound a week, roughly.
Roughly, yes. Now, beyond just weight, we also need to consider malnutrition. This isn't just about being underweight, it's about nutrient deficiencies. Severe forms of protein energy malnutrition, PEM, include conditions like kwashiorkor. This is primarily a protein deficiency, often seen even when calorie intake might seem adequate. It leads to characteristic swelling or edema, particularly in the belly. Then there's marasmus, which is a more severe overall deficiency of both calories and protein. This leads to profound muscle wasting and emaciation. Individuals look skeletal. It's devastating. And as our text points out, these conditions can unfortunately have both genetic predispositions, making someone more susceptible, and strong environmental components like poverty or famine, #####E, other dietary requirements.
The essentials. But it's definitely not just about calories and the big three macronutrients, is it?
Mm.
Carbs, fats, proteins. Our bodies require a whole host of other compounds, often in much smaller quantities, to truly thrive.
You're absolutely right. This brings us to the micronutrients. They might be micro in quantity, but they're definitely not micro in importance. The unsung heroes of metabolism, really. First, vitamins. These are diverse organic molecules, meaning they contain carbon. They're required in very tiny quantities for our health, growth, and survival. They're essential because our bodies either can't synthesize them at all or not in sufficient amounts to meet our needs, so we have to get them from our diet. We classify them into two main groups based on solubility. Water-soluble vitamins, which include all the B vitamins like thiamine, B1, niacin, B3, B12, and vitamin C. These generally are not stored in the body in significant amounts. Any excess is usually excreted in urine, so you need a regular intake, pretty much daily for most, to replenish them.
Okay, water-soluble, need them regularly.
Then there are the fat-soluble vitamins, that's vitamins A, D, E, and A, D, E, K. These are absorbed along with dietary fats. And because they're fat-soluble, they can be stored in the body, primarily in your adipose tissue and liver. A lack of any of these vitamins can lead to specific, often severe deficiency diseases. For example, a deficiency of vitamin C causes scurvy-think bleeding gums, poor wound healing. Inadequate vitamin D can cause rickets in children, resulting in soft, weak bones. An important point, especially for fat-soluble vitamins because they can be stored, is the concept of a tolerable upper intake level, UL. This means excessive intake, usually from supplements, can actually cause adverse effects, sometimes toxicity. More isn't always better.
Right, you can overdo some vitamins.
You can. The clinical example of Percy V that we'll touch on later really highlights this interconnectedness.
All right.
He exhibited low vitamin B12 levels, but this wasn't isolated. It critically contributed to his iron deficiency anemia and his overall poor protein status. This case clearly shows that multiple micronutrient deficiencies often go hand in hand and can exacerbate each other.
The cascade effect.
Exactly. Moving on to minerals. These are inorganic ions, meaning they don't contain carbon, and they are also required in our diet. Essential. We classify them based on the amount needed. Macrominerals are needed in larger quantities. Think calcium, phosphorus, potassium, sodium, chloride, magnesium, sulfur. And then microminerals, or trace minerals, required in much smaller amounts, things like iron, iodine, zinc, selenium, copper, manganese, fluoride, chromium, molybdenum. Tiny amounts, but still crucial.
Macro and micro minerals.
Right, and these minerals have incredibly diverse and vital functions. They act as structural components. Calcium in bones and teeth is the classic example. They function as critical electrolytes, like sodium and potassium, essential for fluid balance and nerve impulses. They're core components of enzymes and proteins, like iron and hemoglobin, which carries oxygen in your blood. And they regulate countless metabolic processes. Deficiencies can be severe. Prolonged calcium deficiency can contribute to osteoporosis, brittle bones. Iron deficiency is a very common cause of anemia, leading to fatigue.
So vitamins and minerals absolutely key.
And of course, we absolutely cannot forget water. Sounds basic, but it constitutes a huge portion of your body weight, often more than half, maybe up to 70–80% in infants. It is absolutely crucial for maintaining overall physiological balance. Without adequate water, all these intricate metabolic processes, all the transport, all the reactions, they would simply grind to a halt. Hashtag dietary guidelines and xenobiotics, what to eat and what to avoid.
Okay, so beyond just getting enough of all the good stuff, the macros, the micros, water, there are also general guidelines on how to eat and maybe what to be cautious about, right? It's not just about avoiding deficiency, but optimizing for long-term health.
Precisely. General dietary recommendations really emphasize establishing a healthy overall eating pattern rather than focusing on single nutrients in isolation. This means maintaining an appropriate calorie level to balance your energy intake with your expenditure and incorporating moderate physical activity into your daily routine. Find that balance. The core focus is generally on nutrient-dense foods, lean proteins, a wide variety of colorful fruits and vegetables, whole grains instead of refined ones, and low-fat or fat-free dairy options. It also strongly advises on foundational food safety practices, proper handling, cooking temperatures to avoid foodborne illness.
Makes sense. Basics first.
Right. When we look at specific macronutrient guidelines, the recommendations often suggest that carbohydrates should typically make up around 45% to 65% of your total daily calories. But the emphasis here is strongly on complex carbohydrates from vegetables, fruits, legumes, and whole grains, while actively limiting added sugars, the sugars put into processed foods and drinks, which offer calories but little other nutritional value.
Quality over quantity for carbs.
Definitely. For fats, the suggestion is usually in the range of 20% to 35% of total calories. Again, with a focus on quality-consuming unsaturated fatty acids like those found in olive oil, avocados, nuts, and seeds, and actively limiting saturated fats found mostly in animal products and some tropical oils, and especially trans fats, often found in processed baked goods and fried foods. It's also noted that while our bodies synthesize cholesterol, high levels of dietary cholesterol might be linked to an increased risk of atherosclerotic heart disease in some individuals, although this is a complex area.
Okay, focus on unsaturated fats.
Primarily, yes. As for proteins, the general recommendation for adults is approximately 0.8 grams per kilogram of body weight per day. This can vary based on age, activity level, health status. And again, emphasis on high-quality protein sources, those that provide all the essential amino acids, meaning the ones your body can't make itself. Think lean meats, poultry, fish, eggs, dairy, legumes, tofu. And then there's another important category of compounds we encounter, xenobiotics, a bit of a technical term. These are broadly defined as chemicals that are not naturally found or expected in the body and don't have any nutritional value. Xeno means foreign. They can be introduced through the air we breathe, the water we drink, or the food we eat. Think environmental contaminants like pollutants or pesticides, or even some food additives or components of plastics. Our body has sophisticated detoxification pathways, mainly in the liver, to deal with these. Dietary advice often stresses choosing foods that help support these pathways and protect against potential harm from xenobiotic compounds. Often, this points back to fruits and vegetables rich in beneficial phytochemicals and antioxidants.
Okay, theory's great, but let's bring these complex concepts to life with some real-world examples. The text gives us several patient profiles that really illustrate these metabolic principles in action. It helps make it concrete.
These cases are invaluable, absolutely. They help us connect the biochemical dots to real people, real health outcomes. Take Percy V, for instance. He was a 59-year-old school teacher presenting with increasing fatigue and significant weight loss. His lab results painted a very clear picture. He had iron deficiency anemia, low vitamin B12 levels, and low serum albumin. Albumin is a major protein made by the liver, so low levels are a strong indicator of protein malnutrition. Percy's case powerfully illustrates the dire consequences of inadequate dietary intake, but also the complex interplay. His low B12 likely worsened his anemia, and his overall poor nutrition led to the protein deficit. It shows how one problem can cascade.
Not just one thing wrong, usually.
Often not. Then there's Otto S., a 25-year-old medical student. His case was more about weight management. He was overweight, successfully lost weight through diet and exercise changes, and the case discussed planning for relapse prevention. This highlights the practical application of understanding DEE, calorie balance, and the behavioral aspects of maintaining a healthy weight. And then Ivan A., the 56-year-old accountant we mentioned earlier, he provides a really stark example of the challenges associated with obesity and metabolic dysfunction in middle age. He exhibited central obesity, that apple-shaped fat carried around the middle, along with high blood pressure, hypertension, abnormal blood fats, hyperlipidemia, and type 2 diabetes. This cluster is often called metabolic syndrome. Ivan's case is a critical reminder of how prolonged dietary imbalances, perhaps excess calorie intake, poor food choices, maybe lack of activity, can lead to this cluster of serious chronic diseases. His very high total serum cholesterol and elevated blood pressure are major risk factors. It underscores the profound link between our diet, our metabolism, and our long-term health outcomes. It's not just about weight. It's about metabolic health.
And the fourth case.
Ann R.
Yes, Ann R. She was a 23-year-old who was severely underweight, diagnosed with anorexia nervosa. She was experiencing fatigue and other complications. Her case exemplifies severe protein-energy malnutrition, PEM, but with significant psychological components driving the illness. It emphasizes that metabolic issues often require integrated medical and psychiatric care. Her situation highlights the extreme end of energy deficit and its consequences.
All right, so we've laid a really solid groundwork. We know what fuels are, how we store them, how we burn them generally. Now, let's zoom in on a specific crucial metabolic state, the fed state. What precisely happens inside your body right after you've had a meal? When your system is literally swimming in freshly absorbed nutrients, It's a busy time metabolically. It's a very busy time. The fed state, also called the absorptive state, is defined as that period following a meal when dietary components are actively being digested and absorbed into your bloodstream. During this time, your body is receiving a significant influx of nutrients, glucose, amino acids, fats. It's a state of metabolic abundance, you could say. And this state is characterized by really crucial hormonal shifts, primarily orchestrated by your pancreas. It's the control center here. When blood glucose levels inevitably rise after a meal, especially one containing carbohydrates, the beta cells of your pancreas swiftly respond by releasing the hormone insulin.
Insulin comes out.
Insulin comes out. And insulin is the predominant anabolic or building up hormone of the fed state. It acts as a powerful signal, almost like a key unlocking doors. It instructs various tissues throughout your body, muscle, fat, liver, to take up glucose from the blood. It also signals them to synthesize glycogen for storage and even to store fat, basically put this fuel away. Conversely, the release of glucagon from the alpha cells of the pancreas is significantly suppressed in the fed state. Glucagon's main job is to raise blood glucose, which is clearly not needed, in fact counterproductive, when glucose is already plentiful.
High glucose site, high insulin, low glucagon. That's the fed state signature.
That's the key hormonal signature. So insulin really is like the body's meticulous storage manager during this period, directing all that incoming fuel to either be used immediately for energy or efficiently packed away for later use. #B, digestion and absorption, getting fuel in.
Okay, so insulin is the manager, but before it can manage the fuel, that fuel first has to get in and be properly broken down, right? How does that happen again, quickly?
Exactly. Let's briefly recap how these dietary fuels are prepared for absorption in the gut. For carbohydrates, the complex starches and disaccharides, like sucrose or lactose, are digested down into their simplest units, the monosaccharides. That's mainly glucose, fructose, and galactose. This is done by a series of digestive enzymes like amylase in your saliva and pancreatic juice, and enzymes like lactase or sucrase in the intestinal lining. These monosaccharides are then absorbed by the cells lining your small intestine and transported directly to the liver via a special blood vessel, the hepatic portal vein. Liver gets first dibs.
Okay, carbs, simple sugars, liver.
Right. Proteins undergo a similar breakdown. They are first denatured, unfolded by the strong acid in your stomach. Then they're chopped up into smaller peptides and ultimately into individual amino acids by a series of powerful proteases. Enzymes like pepsin in the stomach and trypsin and chymotrypsin from the pancreas, plus others in the intestine lining do this job. These amino acids are also absorbed and, much like the monosaccharides, transported straight to the liver via that hepatic portal vein.
Proteins, amino acids, liver.
Correct. Now, fats are handled a bit differently because they don't dissolve in water, the watery environment of your gut. Dietary triacylglycerols are first emulsified by bile salts, which come from the liver via the gallbladder. Emulsification breaks the large fat globules into smaller droplets, increasing the surface area for enzymes to work. Then they are hydrolyzed, broken down by pancreatic lipase into primarily fatty acids and 2-monoacylglycerols. These smaller fat components are absorbed into the intestinal cells. And here's a neat trick. They are remarkably re-esterified, put back together into triacylglycerols inside those cells.
We break them down just to rebuild them.
Seems counterintuitive, but yes. And these reformed triacylglycerols are then packaged into large lipoprotein particles called chylomicrons. Think of them as transport trucks for fat. Uniquely, these chylomicrons enter the lymphatic system first, not the portal vein. They take a detour, bypass the liver initially, and then eventually enter the main bloodstream to be distributed throughout the body.
So fats take a different road initially. Lymphatics, then blood.
Exactly. A different initial pathway. ####TAXIC, fuel distribution and metabolism in tissues.
Okay, so the fuel is now broken down, absorbed, and circulating in the bloodstream, glucose and amino acids coming from the liver. Fats arriving via chylomicrons. What happens to it then? Let's trace these fuels through the major organs again, thinking about that fed state metabolic roadmap. Where does everything go?
Let's follow this intricate journey, driven largely by insulin signals. Starting with glucose. The liver is that first major organ to encounter the high concentration of absorbed glucose coming via the portal vein. It's a critical metabolic hub. It extracts a significant portion of this glucose. Some it uses for its own immediate energy needs. A large amount, under insulin's direction, is converted to glycogen for storage, replenishing the liver's glucose reserves. This is a glycogenesis. If there's still excess glucose after glycogen stores are filling up, the liver can convert it into fatty acids and then into triacylglycerols. These fats are then packaged into very low-density lipoproteins, VLDL, and released into the blood. VLDL is like the liver's own fat delivery truck.
So liver uses glucose, stores it as glycogen, or converts it to fat for export. Busy place.
Very busy. Now, your brain. Remarkably, it primarily relies on glucose as its main fuel source under normal fed conditions. It's a glucose hog. It continuously oxidizes glucose to CO2 and water to generate the vast amounts of ATP needed for its intense activity neurotransmitter synthesis, maintaining those crucial ion gradients for nerve impulses. It needs a steady supply, roughly 150 grams of glucose per day.
Brain needs glucose. Got it.
Your red blood cells, RBCs, are unique. They lack mitochondria, the cellular powerhouses where most ATP is made using oxygen. This means they cannot perform aerobic respiration. Instead, they exclusively rely on anaerobic glycolysis. They break down glucose only partially, producing a small amount of ATP and converting the end product, pyruvate, into lactate. This lactate is then released back into the blood. They live solely on glucose, anaerobically.
RBCs, anaerobic glucose burners.
Correct. Now, your muscle cells, they respond strongly to insulin. In the fed state, they eagerly take up glucose from the blood. Much of this glucose is converted to glycogen for the muscle's own future energy reserves, especially important for fueling exercise. Muscle can also oxidize glucose directly for immediate energy needs. Lastly, in adipose tissue, your fat cell's insulin has a very powerful effect. It greatly stimulates the transport of glucose into these cells. Here, the glucose isn't primarily stored as glycogen. Instead, it's mainly used through glycolysis to produce a molecule called glycerol-3-phosphate. This glycerol backbone then combines with fatty acids, which might come from chylomicrons or VLDL or be synthesized, to form and store large amounts of triacylglycerols, filling up the fat stores.
So glucose helps fat cells make more fat in the fed state.
Exactly. The real aha here is seeing how insulin brilliantly orchestrates this whole body effort. It pushes glucose into cells that need it or can store it, preventing blood sugar from getting dangerously high and promoting energy storage for later. Now for fats, the triacylglycerols being transported, those chylomicrons carrying the dietary fat from your intestine circulate in blood. On the walls of capillaries, especially in adipose tissue and muscle, there's an enzyme called lipoprotein lipase. LPL. Insulin helps activate LPL. LPL hydrolyzes the triacylglycerols in the chylomicrons, releasing fatty acids. These fatty acids are then taken up by the nearby adipose cells for storage, re-esterified into triacylglycerols, or by muscle cells for immediate energy. The chylomicron remnants, now smaller and relatively richer in cholesterol, travel back to the liver to be cleared.
So LPL unpacks the fat from chylomicrons for tissues.
Precisely. Similarly, VLDL, the fat delivery trucks made by the liver, also encounter LPL in peripheral tissues. Their triacylglycerols were also hydrolyzed, delivering fatty acids to muscle and adipose tissue. As VLDL particles lose their fat cargo, they become smaller and denser. Eventually, through a series of steps, they contribute to the formation of low-density lipoproteins, LDL. LDL is primarily responsible for transporting cholesterol to tissues, but high levels of LDL are associated with atherosclerosis, plaque buildup in arteries, which is why it's often termed bad cholesterol.
So VLDL delivers fat, and its remnants become LDL, the cholesterol carrier.
In essence, yes. Finally, let's consider amino acids from digested proteins. A good portion of the absorbed amino acids is taken up by the liver on that first pass. Here, they are used for synthesizing the liver's own vast array of essential proteins. They're also used to build other critical nitrogen-containing compounds, like the purines and pyrimidines needed for DNA and RNA synthesis. If amino acids arrive in excess of the liver's immediate needs for synthesis, they can be deaminated, their nitrogen group removed, and the remaining carbon skeletons can be oxidized for energy, or even converted to glucose or fatty acids. That nitrogen removed during deamination is converted to urea by the liver via the urea cycle, making it non-toxic for excretion by the kidneys. This is crucial waste disposal.
Liver processes amino acids, makes proteins, handles excess.
Right. Many amino acids also pass through the liver and circulate to other tissues, like your muscles. These tissues take them up for their own protein synthesis, building and repairing muscle tissue, and for creating other essential nitrogen-containing molecules specific to those tissues.
Let's circle back to Ivan A., our accountant from Chapter 1. His situation, his diagnosis, really seems to highlight what happens when this carefully orchestrated fed state regulation goes wrong. It's not just storing fuel efficiently anymore.
Ivan A's case is a classic, unfortunately common, illustration of metabolic disturbance, particularly relevant to modern health challenges like type 2 diabetes and metabolic syndrome. His diagnosis included hyperglycemia, persistently high blood glucose.
So even after eating, his blood sugar stays too high.
Exactly. It also included hypertriglyceridemia, high levels of triacylglycerols or fats in his blood, and of course the underlying diagnosis of type 2 diabetes. Let's unpack that in the context of the fed state. His hyperglycemia means that after meals, his blood glucose levels remain stubbornly high. Why? In type 2 diabetes, the key issue is often insulin resistance. This means his cells, especially in muscle and adipose tissue, don't respond properly to insulin signals. The key isn't working well in the locks. So glucose isn't taken up efficiently from the bloodstream, leading to those elevated levels, even if his pancreas is initially trying hard and pumping out a lot of insulin.
The manager is shouting, but the workers aren't listening properly.
That's a good analogy. His hyperlipidemia, the high blood fats, specifically hypertriglyceridemia, is also closely linked. With abundant glucose available from the diet, but peripheral tissues like muscle being resistant to taking it up, the liver takes up more glucose. And because insulin action might also be impaired in the liver in complex ways, it tends to convert more of this incoming glucose into triacylglycerols. These fats are then packaged into VLDL particles and released into the blood in large amounts, contributing significantly to his elevated blood lipid levels. Dietary fat coming in via chylomicrons also adds to this lipid load.
So insulin resistance messes up both glucose and fat handling in the fed state.
It really does. And the source also highlighted Ivan A's physical presentation, his waist circumference, describing his apple shape or central obesity. This pattern of fat distribution, where fat accumulates around the internal organs in the abdomen, visceral fat, is known to be metabolically far more problematic than fat stored just under the skin, subcutaneous fat. It's strongly associated with increased insulin resistance, inflammation, and a significantly higher risk for cardiovascular disease. This really underscores how where you store excess fuel matters, not just how much. His case highlights how excess fuel storage, particularly in certain body compartments like visceral fat, profoundly increases health risks and points to a fundamental disruption in how his body manages nutrients in the fed state. The real aha here is seeing how central insulin resistance is. It creates this cascade of problems: high blood sugar, high blood fats, often high blood pressure, transforming the normally efficient fed state from one of careful storage into one of chronic metabolic stress and disease risk.
Now, let's completely flip the script. The meal is long gone. Maybe it's overnight, maybe longer. What happens when our bodies need to stop storing and start digging into those reserves we so carefully built up? We're talking about the fasting state. This is where our incredible internal systems for survival really shine, adapting to fuel scarcity and orchestrating a major shift from storage to mobilization.
Exactly. The fasting state typically begins, let's say, approximately 2 to 4 hours after your last meal, as blood glucose levels start to decline from their post-meal peak and return towards their baseline pre-meal concentrations. An overnight fast, maybe 12 hours without food, is a perfect everyday example of this early fasting phase. By then, our bodies have clearly transitioned into a distinct basal metabolic state, relying entirely on internal reserves.
So the hormonal signals must flip too.
Completely. The immediate hormonal changes are the mirror image of the fed state. As blood glucose levels decline, the alpha cells of your pancreas spring into action, releasing glucagon. Glucagon is the primary hormone of the fasting state. Its main job is to signal the liver, primarily, to start releasing stored glucose into the bloodstream to keep levels stable. Conversely, insulin levels decline significantly. Remember, insulin promotes storage and glucose uptake. So low insulin reduces glucose uptake by insulin-sensitive tissues like muscle and adipose tissue. This effectively conserves the remaining glucose, prioritizing it for the tissues that absolutely need it, like the brain and red blood cells.
So low glucose, high glucagon, low insulin, the fasting signature.
That's the key hormonal switch. During this initial fasting phase, the body employs a few key fuel mobilization strategies right away. The liver rapidly starts breaking down its stored glycogen. This process is called glycogenolysis. Lysis means splitting. It releases glucose directly into the bloodstream. This is the primary mechanism for maintaining blood glucose during the first several hours of fasting. Simultaneously, that high glucagon and low insulin also stimulates the breakdown of triacylglycerols, or fat, stored in adipose tissue. This process is called lipolysis. Lipolysis releases fatty acids into the bloodstream. These fatty acids become a major fuel source for many tissues, like muscle and heart, allowing them to spare glucose. It also releases glycerol, the backbone of the fat molecule. Glycerol is transported to the liver, where it can be used as a building block for making new glucose. #BB, liver's central role.
The liver really seems to step up during fasting, doesn't it? It's like the body's primary control center for blood glucose, managing supply and demand. Let's delve into its multifaceted role here, thinking of it as our basal state or early fasting roadmap.
The liver's role is absolutely central and incredibly dynamic during fasting. First, it's important to reiterate that liver glycogen stores, while crucial initially, are relatively limited. They can only sustain blood glucose for so long. Typically, they become significantly depleted after about, say, 10 to 18 hours of continuous fasting, maybe a bit longer or shorter depending on the person and activity level. Once that happens, the body needs an alternative, more sustainable strategy to keep blood glucose up, especially for that glucose-hungry brain.
Glycogen runs out eventually. Then what?
Then the liver switches gears dramatically and ramps up gluconeogenesis. Remember, genesis means creation. This is the synthesis of new glucose from non-carbohydrate precursors, making glucose from scratch, essentially. The main precursors, the building blocks, the liver uses for gluconeogenesis are lactate, which comes mainly from red blood cells doing anaerobic glycolysis and also from exercising muscle. Glycerol, which, as we just said, is released from the breakdown of triacylglycerols in adipose tissue during lipolysis. And crucially, amino acids. These are primarily derived from the breakdown of muscle protein. Muscle starts sacrificing some protein to provide amino acids to the liver so it can make glucose.
So muscle protein breakdown fuels glucose production in the liver during fasting.
Yes, that becomes increasingly important as the fast progresses. Now, as these amino acids are used for gluconeogenesis, their nitrogen groups must be removed first. Can't make glucose out of nitrogen. The liver efficiently converts this nitrogen into urea through the urea cycle. Urea is much less toxic than ammonia and can be safely transported in the blood to the kidneys for excretion in urine. This prevents toxic ammonia buildup.
Got to get rid of the nitrogen safely.
Absolutely vital. Another critical function of the liver during fasting, especially as it extends, is ketone body production. As lipolysis continues releasing lots of fatty acids from adipose tissue, these become the predominant fuel circulating in the blood. The liver takes them up in large quantities, but the liver's capacity to completely oxidize all these fatty acids for its own energy can be overwhelmed. So it starts converting the acetyl-CoA derived from fatty acid breakdown into ketone bodies. The main ones are acetoacetate and beta-hydroxybutyrate. Interestingly, the liver itself largely lacks the key enzyme needed to use ketone bodies for energy. It makes them, but doesn't burn them significantly.
Why make them if you can't use them?
Great question. It ensures that these energy-rich, water-soluble fuel molecules are exported from the liver into the blood, making them available for other tissues in the body that desperately need fuel during fasting, especially muscle, heart, kidney, and eventually the brain. The liver acts as a ketone factory for the rest of the body. #C, adipose tissue, and ketone bodies.
And what about our vast fat reserves? Adipose tissue. How do they contribute when we're running on empty beyond just releasing that glycerol? Those 15 kilograms of fat must be critical.
Oh, absolutely critical. Adipose tissue continues to be the primary sustained source of fuel throughout fasting. It persistently releases that steady supply of fatty acids via lipolysis, driven by low insulin and high glucagon and other stress hormones. This constant fat mobilization provides a continuous stream of energy to most tissues, muscle, heart, liver itself, allowing them to drastically reduce their glucose consumption. This glucose-sparing effect is vital for protecting the limited glucose supply for the brain and red blood cells.
So fat burning spares glucose.
That's a key principle of fasting metabolism. This brings us back to those ketone bodies made by the liver from those fatty acids. They are, as we said, water-soluble, energy-rich molecules, acetoacetate and beta-hydroxybutyrate. Acetone is also produced, often smelled on the breath in prolonged fasting or uncontrolled diabetes, but it's less important metabolically. These ketone bodies are released into the blood by the liver and readily taken up and used as fuel by various tissues. Muscle loves them, kidney uses them, heart uses them, and most remarkably, as fasting progresses, the brain adapts to use ketone bodies as a major fuel source, significantly reducing its dependence on glucose. As I mentioned, the liver lacks the necessary enzymes to oxidize ketone bodies itself. It's a producer, not a consumer. This ensures they are generously shared with other tissues that can use them.
So ketone bodies are like shareable, water-soluble, fat-derived fuel.
That's a great way to put it. The real aha here is realizing that ketone bodies are not just some emergency backup fuel. They represent a profound metabolic adaptation. Their production and utilization allow our bodies to tap into our vast fat reserves more effectively, protect vital glucose-dependent organs like the brain, and crucially, conserve muscle protein during prolonged periods without food. It's a key survival strategy. And in a clinical context, remember Percy V., our source mentioned he exhibited elevated ketone bodies in his urine, ketonuria, and serum, ketonemia. This metabolic pattern strongly suggests he was in a prolonged fasting or even starved state, indicating heavy reliance on the breakdown of both fat and protein for energy. The ketones were a clear sign of that metabolic shift. ####D. Prolonged fasting is adapting for survival.
What happens if fasting goes on for days, maybe even weeks? Not just an overnight fast or skipping a meal. The body has truly incredible adaptive mechanisms to ensure survival when food becomes severely scarce. It's quite a testament to our biology.
It really is. During prolonged fasting, which we might call starvation, the body undergoes profound metabolic adaptations geared purely towards survival. One of the most critical shifts, as we hinted, is in the brain's fuel source. Initially, in early fasting, the brain relies almost entirely on glucose made by the liver via gluconeogenesis once glycogen is gone. However, during prolonged fasting over days, the brain gradually adapts. It increases its ability to take up and utilize ketone bodies as a major fuel source. Ketone levels in the blood rise dramatically, and the brain starts using them significantly.
The brain learns to burn ketones.
Essentially, yes. It develops the transport mechanisms and enzymes to use them effectively. This adaptation is an absolute game changer for survival. Why? Because it significantly reduces the brain's demand for glucose, and if the brain needs less glucose, the liver needs to make less glucose via gluconeogenesis. This directly spares precious body protein, primarily muscle protein, which is being broken down to supply amino acids for that gluconeogenesis.
Ah, so using ketones saves muscle.
Exactly. This shift leads to protein sparing. By reducing the brain's relentless need for glucose, the body can drastically slow down the rate of muscle protein degradation. While some amino acids are still needed for essential functions and minimal gluconeogenesis, the overall conservation of muscle mass is huge. It allows for much longer survival times. The liver's role also evolves in prolonged fasting. Reflecting the brain's reduced glucose need, the rate of gluconeogenesis in the liver actually decreases compared to the frantic glucose production seen in the early fasting state, after glycogen depletion but before ketone adaptation. The liver continues to produce ketone bodies in large quantities, that's its main job now, and it still produces some urea from the necessary protein turnover, but generally at a lower rate than in the early phases of fasting.
So less glucose production, more ketone production by the liver.
That's the major shift. To assess the severity of protein depletion during starvation clinically, markers like serum albumin and prealbumin levels become very important. These proteins are synthesized by the liver, and their production requires adequate amino acid supply and liver function. Low levels, as we're seen in PERCEIVE, strongly suggest significant protein malnutrition and a poor prognosis. But despite these remarkable adaptations, there are obviously limits to survival. Death from starvation typically occurs when approximately 30% to 50% of total body protein has been lost, often due to failure of vital organ function, like respiratory muscles or heart. This can happen even if substantial fat reserves still remain.
So protein loss is ultimately the limiting factor.
Often, yes. It highlights the absolutely indispensable role of protein for vital cellular function, structure, and enzymes. It underscores the fragility of this survival mechanism when pushed to its absolute extreme.
These adaptations for survival are truly remarkable biologically, but they also really underscore the severe risks of chronic undernutrition and starvation. Let's look again at how this plays out clinically with their patient examples. It drives the point home.
Revisiting PERCEIVE, his case becomes even more impactful in the context of prolonged fasting and advanced protein energy malnutrition, PEM. The text classified him as having grade IPM based on biochemical markers. His significantly reduced serum albumin and prealbumin levels confirm severe protein depletion. Another marker mentioned was the creatinine height index, CHI. Creatinine is a breakdown product of creatine phosphate in muscle, and its excretion is normally proportional to muscle mass. A low CHI, like Percy likely had, indicates significant muscle wasting.
So CHI measures muscle loss.
It's an indicator of muscle mass, yes. Percy's poor absorptive capacity, possibly due to damage to his gut lining from malnutrition, further complicated any attempt at nutritional rehabilitation. His case powerfully demonstrates the dire consequences when the body's adaptive mechanisms are pushed beyond their limits, leading to a breakdown of vital functions and a profound state of illness. Similarly, Anne R's case, the young woman with anorexia nervosa, directly reflects the metabolic state of prolonged starvation, albeit self-imposed. Her extremely low body fat and body weight, her BMI was noted as 13.7, which is severely underweight, forced her body into these extreme adaptive measures: low metabolic rate, reliance on fat, and eventually protein breakdown, ketone production. Her amenorrhea, the absence of menstruation, is a common consequence in severe energy deficit and low body fat in women. It's due to complex hormonal disruptions, essentially the body shutting down non-essential reproductive functions to conserve energy for survival. Her impaired glucose tolerance, sometimes seen in starvation despite low baseline glucose, and low blood glucose levels all indicate a profoundly dysfunctional metabolic state, requiring comprehensive psychiatric and expert nutritional intervention. These cases truly illustrate the devastating human impact when these delicate metabolic balances are severely and chronically disrupted.
And briefly, you mentioned BUN and creatinine earlier.
Right, just as general clinical markers. Blood urea nitrogen, BUN, reflects the urea produced by the liver from protein breakdown. It can be high if there's excessive protein breakdown or if kidney function is impaired, since kidneys excrete urea. Serum creatinine is primarily used to assess kidney function, as it's normally cleared by the kidneys at a steady rate. Elevated ketone bodies in blood or urine, as we discussed, are clear metabolic signals pointing towards fasting, starvation, or poorly controlled diabetes where insulin is deficient or ineffective.
Wow. Okay. We've covered a tremendous amount of ground here. From the immediate aftermath of a meal, that fed state, all the way through early fasting with glycogen use, then gluconeogenesis, and finally into prolonged starvation with ketone adaptation and protein sparing. It's incredibly clear that these three states, fed, early fasting, and prolonged fasting, are not just isolated snapshots. They're deeply interconnected parts of a continuous dynamic metabolic story unfolding in our bodies all the time.
Indeed. What truly stands out when you look at it all together is how the body so dynamically and usually seamlessly transitions between complex and precisely orchestrated dance of biochemical pathways, all designed to ensure your survival and function in both times of feast and times of famine, or even just between Tuesday's lunch and dinner. And this entire intricate system is under the strict command of hormonal orchestration. Hormones like insulin and glucagon acting in opposition are the primary conductors of this metabolic orchestra. They send signals to cells, telling them whether to store fuel or release it, constantly adapting to your body's immediate energy status and its longer-term needs.
The push and pull of insulin and glucagon.
That's the central axis, yes. And understanding these fundamental pathways, this push and pull, it's not just academic biochemistry. It's absolutely vital for comprehending the basis of many, many common diseases and disorders that affect millions. Think about the conditions mentioned throughout our discussion and in the sources summary tables. Obesity, type 2 diabetes, with its hallmarks of hyperglycemia and hyperlipidemia, high cholesterol, hypercholesterolemia, and the various forms of malnutrition like kwashiorkor, marasmus, and the metabolic consequences of anorexia nervosa. These conditions fundamentally represent disruptions, sometimes subtle, sometimes catastrophic, in the delicate balance of fuel intake, storage, utilization, and that crucial hormonal regulation. For example, the insulin resistance that's central to type 2 diabetes means the body can't effectively respond to the fed signal. It struggles to clear glucose from the blood and store it properly, leading to chronically high blood glucose and all the damaging downstream consequences. The profound insight here is recognizing that when these finely tuned, evolutionarily ancient metabolic systems are chronically overloaded, mismanaged, or perturbed, whether by modern diets high in processed foods and calories, sedentary lifestyles, genetic factors, or specific diseases, the consequences for our health can be truly devastating.
It really makes you appreciate the intricate design, doesn't it?
Yeah.
It's mind-bogglingly complex. What stands out most to you about how finely tuned our bodies are, and yet maybe how easily that balance can be tipped by modern life or disease?
It is remarkable, and I think it raises a really important question for all of us, especially anyone studying or working in health. Armed with this profound biochemical knowledge, how can we use it better? Not just to treat diseases after they develop, but to truly promote long-term health and actively prevent these metabolic imbalances from occurring in the first place. It really comes down to empowering ourselves and our patients or communities with this understanding, recognizing that our daily choices, what we eat, how we move, have direct, tangible biochemical consequences. It's about respecting the incredible ancient machinery we inhabit. Hashtag tag tag outro.
And that, my friend, wraps up our deep dive into the fascinating, sometimes bewildering, but utterly crucial world of fuel metabolism. We've journeyed through how our bodies take in fuel, how they cleverly store it, and how they burn it for energy. And we've seen how incredibly adaptable this system is, yet also how fragile that balance can sometimes be. We've covered the central role of macronutrients, carbs, fats, proteins as our primary fuel sources. We've explored the body's really smart and efficient fuel storage system, dominated by fat but relying also on glycogen. We've broken down the constant balancing act of daily energy expenditure, BMR, activity, diet-induced thermogenesis, and, perhaps most critically, we've seen that vital hormonal control, the insulin-glucagon seesaw that dictates whether we're in fed or fasting mode, constantly adjusting to keep us going. It's a truly miraculous internal economy. For a final thought, just consider the sheer biochemical intelligence that allows your brain, an organ utterly dependent on glucose initially, to smoothly shift gears and readily accept ketone bodies as fuel when food is scarce for a prolonged period. It's an amazing testament to millions of years of evolution, a survival mechanism literally built into our cellular software. But it's also perhaps a stark reminder of how our modern diets and lifestyles, often characterized by constant fuel availability and different fuel types, can either profoundly support or subtly undermine that ancient metabolic wisdom. Think about the incredible journey your cells embark on with every single meal, and every period between meals, a constant complex dance of supply, demand, storage, and mobilization. We want to extend a huge thank you to the Last Minute Lecture team for compiling such comprehensive and insightful source material from Marks Basic Medical Biochemistry. It truly made this deep dive possible and hopefully valuable for you. Until next time, keep that curiosity alive, keep learning, and keep diving deep.